Hi everyone, welcome back to my channel, and today I'm going to be talking about real analysis. So what is real analysis in the first place? Real analysis is often considered to be a more rigorous version of calculus. Now it's important to realize that calculus has a lot of applications in the real world. It is used in physics, astronomy, chemistry, biology, engineering, computer science, and a variety of other disciplines. Now, the reason real analysis is called a more rigorous version of calculus is because it proves some of the fundamental notions and concepts in calculus itself. Now, real analysis just does not study a rigorous version of calculus or study the fundamental concepts inside of calculus. Rather, it studies the fundamental concepts of mathematics itself. Yes, it does include the fundamental concepts of calculus, but it studies the fundamental building blocks of all of mathematics, namely an axiom. It studies axioms, numbers, number fields, and etc. So it's important to realize that real analysis is just a study of a more rigorous version of calculus and a study of the fundamental concepts of mathematics itself. Okay, now that we've talked about that, let's talk about what an axiom actually is. So what is an axiom in the first place? Because an axiom is very important. Now, if you've taken Euclidean geometry, you probably know what an axiom is. It is a statement that we fundamentally agree upon. So an axiom, in other words, is something that we assume. But in mathematics, axioms are very important. The reason? Mathematics is just an axiomatic system. We can say that math is an axiomatic system. So in other words, it's based upon some fundamental statements that we all assume to be true, and then it draws conclusions from those specific statements, and then builds upon like a tree after that. So if we have some dots, it creates more dots. And keeps on going forever and ever and ever. So mathematics is just an axiomatic system. Now Euclidean geometry, which essentially just draws conclusions from an axiomatic system, which Euclid created and then he drew conclusions upon, is a very important subject in mathematics. And Euclidean geometry is based upon an axiomatic system. And real analysis talks about some of the most basic axioms at the beginning. Now, over here we have 5 axioms. We have the commutative law, the distributive law, associative law, identity law, and inverse law. Now, these 5 axioms form a field. Now, we'll talk about what a field is in more detail in the next video. But it's important to realize that these are some of the most fundamental laws, and axioms specifically, that we know about. Most of you have probably heard it when you studied in school. So, first we have the commutative law. The commutative law states that A plus B is equivalent to B plus A. In other words, if you have 1 plus 2, this is equivalent to 2 plus 1. This is an obvious fact. The distributive law states that we have A times B plus C, where B plus C is in parentheses. This is equivalent to A times B plus A times C. So let's just say we have 4 times 3 plus 2. If we simplify the arithmetic expression inside of the parentheses, we get 5, and we have to multiply that by 4, and we get 20. Now, if we use the distributive law, we have 12 plus 8, because 4 times 3 is 12, and 4 times 2 is 8. Therefore, we get 20. So as you can see, the distributive law also works. Now we'll talk about these axioms in more detail in relation to a field in the next video. But let's continue. So we have the associative law. So consider that we have A plus B plus C. Or let's draw an example. We have 1 plus 2 plus 3, and we put 1 plus 2 in parentheses. Calculating this, we get 3 plus 3, and we get 6. So 6 is our answer. Likewise, if we do 1 plus 2 plus 3 again, but put parentheses around the 2 and 3, we get 1 plus 5, which is also equivalent to 6. So in other words, A plus parentheses B plus C is equivalent to parentheses A plus B and parentheses plus C. Okay. Okay, so after that we have the identity law. So if we have A, which can stand for any number, and we add 0 to that number, we are always going to get A, the original number itself. So if we have 54, adding 0 will give us 54. Likewise, if we have 54, if we multiply 1, we're going to get 54. So this is the identity law. Next we have the inverse law. So the inverse law states that A times 1 over A is equivalent to 1. In other words, 1 times 1 over 1 is equal to 1, and this satisfies. Now if we have 2 times 1/2, this is going to give us 1 as well, because this just gives us 2 halves, which just simplifies to 1. So as you can see, the inverse law also is satisfied. And we can do the same thing with addition. So we have 5, subtract by 5, we get 0. A subtract by A is equal to 0. Now you might be wondering the reason why I said subtraction is addition, because if you think about it, A minus A is equivalent to A plus negative A, where negative A can be considered as a negative number itself. It's not considered as an operation, rather it's considered as a negative number itself. So we can consider subtraction to rather just be the addition of two different types of numbers, rather than considering subtraction as an actual operation. Okay, so that's what an axiom is. An axiom is a statement that we fundamentally agree upon, and it's important to realize that mathematics is built upon this axiomatic system. Now let's talk about one of the most important things in mathematics and most important collections if we think about it, which is namely a set. So what is a set? Well, a set can be a collection of pretty much anything. Now in mathematics, you use numbers when talking about sets. So let's talk about some of the basic notions for a set, and then in the next video we'll talk about a more deeper understanding and a more deeper level of a set itself. So sets are usually labeled with the capital N. And then we put these curly braces, and we say, or we specifically write, the numbers inside of them. Now, this is set A. Set A has elements 1, 2, 3, and 4. Now let's say we want to say that 3 is in the set A. To say that 3 is in the set A, we say 3, and we put the symbol, and then we write A. This states that the element 3 is in the set A. Now, if we do it with 5, we know that 5 is not in the set A. So we can write it like this. Okay, so this is the basic notion of a set. Now there are finite sets and infinite sets. Infinite sets, or likewise the name suggests, means that there are an infinite number of elements, where finite sets just have a specific set or specific number of elements. Furthermore, sets can have other properties and operations if we say for them to have. For example, we have the union symbol, or you can consider it the union operation. So let's say we have set A, and we have set B. Now set B has the elements 5, 6, 7, and 8. Now if we union them, we have A union B, which is equivalent to the set 1, 2, 3, 4, 5, 6, 7, and 8. Now that we've talked about that, let's consider another pair of sets. Let's consider the set K, which is equivalent to 3, 4, and 7. And this set R, which is equivalent to 5, 7, 9. Now let's say we want to find the intersection. As the name suggests, we have K intersecting R, or the intersection of K and R, which is just this set 7 with one element, because 7 is shared by both sets. Okay, now that we've talked about some of the fundamental notions of sets, let's talk about proofs. Now in real analysis, as described earlier, the reason real analysis is considered a more rigorous version of calculus is because it uses proofs and proves some of the fundamental concepts in calculus itself. Now, are proofs really necessary? Now, if we have an axiomatic system in mathematics, and we draw conclusions from this axiomatic system, then we want to know if this conclusion from this axiomatic system is true or if it is false. We could have a very broad generalization that makes it false. So we want to test if it is true or if it is false. And we have to test it and prove it by the axioms, by the standards set by the axioms. So proofs are necessary in real analysis. This is what makes real analysis a rigorous subject, because it involves so much proofs. Even if mathematics is built upon an axiomatic system in which we assume many things, mathematics wants to prove everything set by the standards of the axiomatic system. Now that we've talked about that, let's recap. So first we have real analysis. So what is real analysis? Real analysis is not just a study of a more rigorous version of calculus, rather it is also a study of the fundamental concepts of mathematics, which are axioms, sets, number fields, and etc. Next, what is an axiom? An axiom is a fundamental statement that we all agree upon and that we assume. Now, mathematics can just be drawn to an axiomatic system. Either that we have a set. A set is a collection of primarily anything. Now, we can have an infinite set or a finite set. An infinite set has an infinite number of elements, and a finite set has a finite number of elements. Lastly, we have what are proofs and what are they used for. Proofs are essentially just a set of processes trying to prove a specific statement, and they're used in real analysis to essentially show the validity of specific theorems, concepts, and etc. Rather, they're used in a lot of branches of mathematics. Now that we've talked about that, we can make this video to an end. If you like this video, if you like this channel, please subscribe to learn more. Thank you.